Okay, so to wrap up on torque, the last thing we need to talk about before you do some questions is called the center of mass. Okay, so if you think of a uniform object, like a ruler or a meter stick, and if you think there's a little increment of mass on this side that has an FG acting down, but there's an equal increment on this side that has an FG acting down. And these two FGs are going to balance each other out or cancel each other out. Then we could do another increment on either side that would do the same thing, and another, and another, and another, until finally you get to the very middle. And so then because both sides are all balanced out, it looks as if all the mass is acting on this spot. And so we say this is the center of mass of the object, and we say that that's where the gravity, it looks like gravity is acting. Okay, so the definition of center of mass then would be the point on the object where all the object's weight appears to be acting. The point on the object where all the object's weight appears to be acting. And if the object is uniform shape, it'll always be in the middle. But the object might not be uniform shape. Not many of us are. So the object might look like this. Well, I could still find the center of mass experimentally, because I could take part of the mass on this side and an equal piece on this side, so they'd balance each other out, and then another sliver here and an equal piece here and another sliver here. And so we could still experimentally find the center of mass. It's just not going to be in the center of the object. It'll be shifted some, right? It'll probably be here. So whenever it's not a uniform object, if it's something like my stapler, you can find the center of mass experimentally by just finding the spot where it balances. But in a question, whenever it says the object is uniform, what they're telling you is that the center of mass is in the middle of the object. Your job is to remind me that, one, we need to go into the hallway to find our own center of masses, and two, I need to show you a toy that I have that will help you appreciate center of mass. Center of mass becomes important if you're an athlete, right? Depending on the athlete. If you're running in football, if you're skating in hockey, the coaches will always tell you to crouch. You crouch to keep your center of mass low. It makes it harder for someone to knock you over if they don't have a big distance to hit you from. The center of mass will be the point where you'll rotate around. So if you're crouched low, then none of you is far from that, and so it's hard to make the torque big. If you're a gymnast, you need to know where your center of mass is so you can balance. If you're a figure skater in pairs figure skating, remember the guy that always picks the girl up and puts his hand on her tummy area and swings her around. His hand has to be on her center of mass or it's not going to end well. For stereotypically, a male center of mass tends to be higher because males tend to be more muscular in the shoulders, right? Not as uniform. So their center of mass would be shifted more towards their shoulders because they would be bigger up here and narrower at the waist. So their center of mass would be higher. It's usually somewhere around like your breastbone. Females, our center of mass tends to be a bit lower. It tends to be more around our hips because we tend to not have as many shoulder muscles, but our hips tend to be bigger because of the whole childbearing thing, getting us ready to have children. That's stereotypical. Obviously, we're all in different shapes, both muscle-wise and body fat-wise. So so for females, our center of mass tends to be closer to our belly buttons, and males, yours tends to be closer to your breastbone. But depending on our shape and our fitness and stuff, it could be anywhere in between there. So one of these days next week, we'll go out into the hallway and we'll do a few activities to find out where is your center of mass, okay, compared to the other people's in the classes, all right? And it'll be kind of fun. There's a few, because depending on where our center of mass is, there are some things that will be easier for us and some things that'll be more difficult, okay? So that's center of mass. Now, maybe I gave you, do I want to do an example? I gave you a sheet with an example. I'm pausing because I don't have it in front of me. It had the definition of center of mass on it. And then and I'm just looking for it. And then it had 3 examples. So the first one says 2 children, only I could reach it. 2 children are sitting on a seesaw of length 5 meters and with a mass of 10 kilograms. Okay, so here's my seesaw. Length 5 meters, mass 10 kilograms. Fulcrum is placed in the middle. Here's M1, here's M2. After this, I probably won't actually draw the kids in. I'll just draw in their forces, FG1 and FG2. Now, what's changing here from all the other units that we've done is that we're looking at the forces on the board. We don't really care about the kids. We only care about the force they put. So we're looking at all the forces that are on this seesaw plank. And that's what we're going to look at them to see. Do they balance out? Is it going to rotate? Is it going to stay in balance? Okay, so the 2 kids are putting forces down. The fulcrum is putting a force up, and the weight of the board itself is acting on the board. And because I think it says a uniform board, it'll be acting smack dab in the middle. The seesaw is perfectly balanced at the fulcrum, placed at the middle of the length. One child is 46 kilograms, 2.2 meters from the fulcrum. The second child is 1.8 meters from the fulcrum. Okay, so child 1, child 2, R1, R2. So this is 2.2 meters, this is 1.8 meters, and I think this was 46. Yeah, kilograms. Okay? The fulcrum is halfway along its length where the center of mass will be. If we do our sum of the torques, in theory, 4 torques, all 4 torques all 4 forces could create a torque. So there would be the torque from kid 1, the torque from kid 2, the torque from the board, and the torque from the fulcrum. But when you take a look, the board and the fulcrum are going through the pivot point. So both of these torques are going to be 0 because their R's are 0. Remember, torque is RF sine theta. So if R is 0, the torque's going to disappear. Kid 1 is going to make this board rotate counterclockwise, which would be positive. Kid 2 is going to make this board rotate clockwise, which will be negative. So then we'd end up with R1 FG1 sine theta 1 minus, that's an R2 FG2 sine theta 2 equals 0. What's the angle between the R and the F? They're going to be 90. Sine of 90 is 1. So this will become R1 M1G minus R2 M2G equals 0. And you're solving for M2. The G's will cancel. R1 M1 equals R2 M2. M2 should equal R1 M1 divided by R2. Okay, and then just fill in your numbers. So 2.2 meters, 46 kilograms, divided by 1.8 meters. And when you do this, you should get a mass of 56.2. And the 2 might be repeating, but I'm not sure because I can't do it in my head. Times 46 divided by 1.8. It is 56.2 repeating kilograms. Okay? It's just that easy. So the ones I'll give you for the first night will be that easy, and then we'll move on. Okay? Very good.